All right, let's look at page 3 of exam 1. And here we're looking at some mechanisms. And in the first one here, we've got an ether and we've got an acid. All right, so let's walk through our mechanism here, right? Oops. There we go. And we got HBr. Okay. So nothing too surprising for the first step. If you have an acid, make it act like an acid. All right, so our ether is going to reach out, grab the hydrogen, you make a bond, you break a bond. Oh, let's use blue here. Okay. There's our aromatic ring, there's our oxygen. So far so good. Bond in purple to our hydrogen. And we've got bromine here, or I should say bromide. Okay, so we protonated our ether. So remember, a protonated oxygen is going to make a good leaving group, right? Or I should say a protonated oxygen with a positive charge. So we have two choices. We can hit the blue, or we can hit the yellow carbon. Because the next step in our mechanism is our incoming nucleophile, the bromide, is going to hit the carbon next to our leaving group and hit the carbon next to our leaving group, right, and cause an SN2 type mechanism to happen. Well, we've got an issue. So our blue carbon is attached to an aromatic ring. You are not going to do an SN2 reaction in an aromatic ring under these conditions, right? You're not going to be doing an SN2 reaction on most aromatic rings anyway. But especially not under these conditions here. So we really only have one choice, right? We are not going to be reacting aromatic rings until we get into the next couple of chapters, right? And even then, we have to have special conditions. So not under these conditions are we going to do anything with the aromatic ring. So we're going to ignore our carbon in blue. And so instead, we're going to hit there. You make a bond, you break a bond. And we get our products. There's our oxygen and the purple bond to a black hydrogen. There's our alcohol, which gets formed. We have, let's draw it like this. We ended up making a purple bond to a bromine. Wonderful. Okay. And if we just want to follow along, there is our yellow and there is our blue carbons there, just so we're kind of tracking along. Okay, so simple, right? This is an acid catalyzed cleavage of an ether, right? If we didn't have that aromatic ring right there attached to the ether, then we could have gone through another equivalent of this, okay? But so far, there we go. Okie dokie. Now we've got acidic conditions and an epoxide, right? So this is going to be similar to what we saw in the previous video, right? We walked through a mechanism with acid catalyzed ring opening. So first step, let's grab that hydrogen. All right, there it is. Now remember, if we're doing acid catalyzed ring opening of an epoxide, we're going to undergo what we call the SUMO condition, right? We're under SUMO conditions, where, let me put parentheses around here, where basically what's happening is the oxygen is pulling to one side, right, and leaving behind the positive charge. Right, so the oxygen is pulling to one side to relieve the strain by weakening the bond there, which I'll put with the dotted line, by weakening the bond there and leaving behind the positive charge. So under acidic conditions of ring opening, we have to pick, right, which one of those positives is going to be the most likely to form. Right, so it's just like with a carbocation, where the carbocation is going to form at the most substituted. But remember, what we're really saying is when we talk about most substituted, we're saying wherever it's the most stable, right? Wherever it's the most stable. It just so happens that this carbon right here, right? This carbon right here That is what's known as a benzylic carbon. It's the carbon that's next door to a benzene ring, right? What happens if we draw a positive charge there, we can actually start to draw a resonance structure. So that benzylic carbon is going to be stabilized by being next door to that benzene ring there. So we're going to end up picking this one to work with, right? So here's what I mean. So I'm just going to redraw this down here. Remember, with this mechanism, we don't completely pop open that ring, right? We don't completely pop open that ring. Our incoming nucleophile comes in and then opens the ring that way. But our incoming nucleophile is going to hit the more substituted side. So, excuse me, not the more substituted, the more stable side. Okay, so we're going to hit the more stable side, right, which was this guy here. Right, the positive charge on that carbon in green there, right, it's going to be more stable over there. So let's draw what happens next. All right, so now we got this. We opened up our ring and made a bond to our alcohol. Okay, and then for the last step, probably more of our acid, more of our alcohol, or maybe even another epoxy. Whoops, getting ahead of myself. More of our alcohol is going to come in and clean things up. And so our final product is a ring opening where we form an ether. And we form an ether and an alcohol next to each other. Great, there it is. Okay, and just to track along, right, there's my green carbon there. So remember, ring opening, we're going to hit wherever the most stable positive can get formed. So I'll zoom out here. There's page 3, and on the next video we'll do page 4 then.